Hello and welcome to the last video on vectors. We talked about lines in 2 dimensions. Today we're talking about lines in 3 dimensions. So when we talked about 2 dimensions, we have this form over here, which we were familiar with. And we thought, well, there is another way to write this. And we figured out the vector equation. But we figured out that maybe this was a bit non-practical, not that useful. Well, in 3 dimensions, the vector equation is really going to be important. So again, how is this going to work? We're going to have a position vector just to get to the line, and we're going to have a direction vector to move along the line. So if for example, if you need to calculate the line between 2 points, here they are, P and Q, how would you do that? Well, quite simply, use the vector position OP as your position vector. That'd be vector 1, 2, 1. That takes me to point 1, 2, 1. And PQ could be my direction vector because that moves from a point in the line to another point in the line. So PQ is a perfectly good direction vector. And hence, OP is this, PQ is minus 2, minus 2, 2. So finally, the equation of the line would be 1, 2, 1, my position vector, plus lambda, again, my parameter that I'm going to change. And it's going to change how big or small or which way it's going, my direction vector. And adding these two vectors together, I would get to any point I want to in the line and nowhere else. So that's an equation of a line in 3 dimensions using the vector equation of the line. Here's a bit of a graphic representation. It's not very clear, but you'd have your x-axis be the red one, your y-axis is the green one, your z is the blue one, and points P and Q could more or less be around here, and here you'd have the line in 3 dimensions. So what do we do with it? Well, first of all, we have to think about what the implications of the lines in 3 dimensions are. And most importantly, do they cross? Always. You see, lines in 2 dimensions will cross in 2 dimensions unless they're parallel. But in 3 dimensions, this is a different story. So what's going to happen in 3 dimensions? Well, the answer is that they don't necessarily have to cross, meaning by crossing that they actually have a point in common. I have these 2 lines over here. I know it's a bit hard to see, but these 2 lines here do not necessarily share a point. They kind of go past each other without actually sharing a point. So we say that they do not cross at a point. And they don't have to be parallel if they don't do so. They might be parallel, they might not be parallel, but that does not mean that they cross or don't cross. So we learn how to solve, we will do the following thing with 3-dimensional lines. We will learn how to solve real-life problems with them. We will learn how to calculate the angle between 2 lines, whether they cross or they don't. Let's find the point of intersection of 2 lines, for example. So here I have line R and line S, and here I have my vector equations of them. So how do you do that? Well, essentially, there's a point in common x, y, z between the 2 lines, right? So there's a value of lambda here and a value of mu here. And with those 2 values, I'm going to have to get the same point, right? And that same point must be both in R and in S. So all I have to do is write in simultaneous equations like this, because I need 2 plus lambda to be equal to 5 plus 2 mu, and so on. This 3 systems of equations only has 2 unknown variables. So what I have to do is simply solve it with the first 2, and I get that mu is equal to minus 1, and I get therefore the lambda is equal to 1. Just of the system of equations. Now what I can do now is check in my third equation, because you see if I put lambda equals 1 here and I put mu equals minus 1 here and I get a different number, well, that would mean that it doesn't work, right? It didn't quite work. That would mean that the equations the 2 lines did not have a point in common. They don't touch. But if actually it works, like in this case here, when I substitute with the 1 and the minus 1, I get that it's the same thing. I get that 4 equals 4, meaning that the two lines actually share a point in common. So that's basically how it works. And of course, I still need to figure out the actual point of intersection. I haven't done that. I figure out what value of lambda and what value of mu I needed for the 2 lines to intersect, but I haven't actually figured out the point. So all I have to do is just pick up the lambda, for example, equals 1, and substitute in here, and I get 0.304, which is the point where these 2 lines intersect. So how do I calculate the angle between 2 lines? Well, the important thing here is that the only lines that are the only vectors that are going to matter are the direction vectors, because the direction vectors are going to tell me basically what the orientation of the line is. The position vector just tells me where it is. So all I need to do is calculate the angle between the direction vectors. And I can do that using my good old scalar product formula. So I'd get in the cosine is equal to 0.477, and hence if I put it in degrees, it was 61.5 degrees approximately. Remember, the formula is in your booklet, and you can use it from there. No need to memorize this big monster here. Finally, let me give you an example of a typical exam question. Here I have two lines, right? And they ask me to find out A and B so that these two lines are parallel. Now, what is that going to be? Well, if the two lines are parallel, what I'm certainly going to need is for the two direction vectors to be what? Parallel. So, in order for two vectors to be parallel, remember they must be proportional. So what do? I simply have to figure out that A divided by A divided by 1, here it is, A divided by 1 must be equal to 3 divided by 2, which must be equal to B divided by minus 2. And hence I can get my direction, the parameters of A and B, so that this vector is parallel to this one. Here's another example, and this is a real life situation, okay? Suppose I have a position of a helicopter, okay, and it's right after takeoff. So of course it's taken off the ground, which is why the position vector here is 1 minus 1, 0, because the altitude is 0. And after t seconds, so here I'm going to put my time, you see my lambda now actually means something, it means time, and its position is given by this line equation over here. So if we know the result of the equation, like for example 1 minus 1, 0 means 1 on the x-axis, minus 1 on the y-axis, but that means 1 meter on the x-axis, minus 1 on the y-axis. So knowing that this equation to meters, find the speed of the helicopter and find the altitude after 3 seconds. Well, actually, that's not very difficult, because you see, this is the position vector. This is how much am I moving. So how many meters per second am I moving? Well, this helicopter is moving. The direction would be like a vector is 2, minus 1, and then 3 going up. So you calculate the modulus of this, you're going to get the speed. Let's do it. So I know that it's square root of 9, which is 3 meters per second, because t, remember, is seconds, and these units are in meters. So the altitude after 3 seconds, well, all I have to do is realize, well, this is when time is 0. So when time is 3, I'm going to get z, which is giving me the altitude, to be 9. And so the altitude is 9 meters. And that really is not a very difficult question. What's difficult here is to really understand how the vector equation of the line works, and how it's providing us with this sort of information. Thank you very much for watching. I'll see you next time.